Hello everybody, and today we will discuss detection of microarchitectural side channel attacks using thread level performance counters. So I will walk you with the outline of my presentation. First, I will talk about my problem statement, then some brief introduction of the architecture of cache memory. A cache attack will also be discussed, which is flush and reload attack. Then my proposed technique, experiments and results, and finally the conclusion. So in modern processors, we have a cache memory structure that is vulnerable to certain cache side channel attacks. Now, directly moving to the mitigation of these attacks is having a problem, which is it needs certain modification in the hardware, or it needs some software upgrades which cause certain performance impacts, and also the type of mitigation may be dependent on the attack. So instead of that, detection has to be done initially, which ensures that the mitigation is applied only on need basis to serve as first line of defense against such attacks. So let us consider this cache memory structure. Here we can see that there are 4 cores in the processor, and each of these cores are having individual level 1 and level 2 memory. But the last level, which is the third level, is shared across all the cores. So this shared memory can act as a problem to cause the attack when the victim and the attacker are on one of the individual cores. Another property which is exploited by the attacker is that a cache hit or a cache miss has different timings. So if data is present in the cache, the access is faster, and if it is not present in the cache, the access is slower. So this time difference is exploited by the attacker to cause an attack. We will see in this example. This is an algorithm to cause encryption by using an encryption key E. Here, if you can see, the steps 8 and 9 depend on this key value for execution. So the victim will monitor the presence of these steps 8 and 9 in the cache memory. So if it is a cache hit, that means the victim had executed these steps 8 and 9, which means the E value in step 7 was 1. That's how the attacker can retrieve this key value to be 1. And if the steps 8 and 9 are not present in the cache memory, that means the E value was 0, which was executed by victim. So this is how the E value will be extracted by the attacker by monitoring the presence or absence of these instructions 8 and 9 in the cache memory. So in order to detect these attacks, certain performance counters have to be monitored in the system, and high count in these performance counters can detect the attack. But instead of monitoring the entire system's performance counters, fine-grained performance counters have to be designed such that only a certain section in the victim code, which is confidential, has to be monitored rather than the entire application. So this reduces the overall monitoring overhead and also reduces the false alarms. Now, in our implementation, these are the implementation details, and we had performed a cache template attack, which is based on the flush and reload method, and it extracts the key presses of the victim. It was done on 3 different editors, and the monitoring tool was used, which is VTune Profiler. So in our experiments, we saw that these 4 different counters showed exorbitantly high counts in case of an attack. Whereas, and these experiments were conducted in 3 different scenarios. One is the attack case, one is no attack case, where only the victim code was being executed, and one is a no attack system overloaded case, where victim was executed along with some other applications running in the background, which are highly CPU intensive, and there is no attack happening in this case, just to identify if there are any false alarms in this scenario. So these are the experimental results. When the entire system was being monitored, there we can see that the counts are high in case of the attack and the CPU intensive application scenario. So here we can see that there can be some false alarm in the CPU intensive application case, which may detect an attack when actually there is no attack happening. It's just a number of applications running in the background, because of which the counts have increased. But when we only monitor a sensitive section of the victim code, and it is a fine-grained monitoring, there we can see that the false alarms are not there. Only in case of attack, the counts are high. So this we saw in case of all the 4 counts. And this finally we can see that there are nil false alarms in case of fine-grained monitoring. And whereas on the system level monitoring, there was 48% false alarms, as well as false negatives are nil, because high level of counts are seen only in the attack scenario, and hence deriving the threshold becomes very easy, and accurate detection takes place, and false negatives are also 0. This is the conclusion that thread level monitoring reduces the false alarm, reduces performance impact due to unnecessary application of mitigation technique, reduces the monitoring overhead also because the only sensitive thread is being monitored, and it also very clear to derive the threshold, hence reducing false negatives. Thank you.